right, thanks. Am I audible today? Yeah? Okay, cool. I was also asked to write bigger, so if at any point it's not readable, just please shout because I can't fix it like after the talk, right? So, okay. So as I said yesterday, what I want to spend today's lecture on is talking about Kuzu Duality for a bit. So for the most part, these are pretty classical ideas by now, so I might be telling you stuff that doesn't look particularly new to you, which could be true. But I have to set it up in a way that works very generally. So in particular, not in a DG context, because that's not going to be very useful when we do periodic stuff. Okay, so the very rough idea, or the general idea here, for Kuzu duality is you can summarize in the following sentence, and I'll try to make this precise. So the idea is whenever you have some algebraic structure, could be anything like commutative algebras, commutative ring spectra, Lie algebras, En algebras. As long as it's parameterized by an operad, there should be some kind of dual co-algebraic structure to that. So for any algebraic structure parameterized by an operad, so for today, I'll use this kind of script O notation for a generic operad. There's always a Kuzu dual co-operad. I'll define the terms, just in case. So there is a what's called Kuzu dual co-operad to this thing. Which might be called BO, or maybe I'll sometimes use the notation bar O. It's obtained by some sort of bar construction. And there's going to be a relation between algebras for this operad O and co-algebras for this co-operad BO. So there's going to be an adjoint pair of functors that relates O algebras to BO co-algebras. Okay, so this is the sort of setup that I want to describe and use. Okay. All right, so let me just maybe specify the context that I would want to work in. So the context will be, we're going to work in a pretty general homotopy theory. So I'm going to fix some base category C, or base infinity category C, and this could be any of the following examples. These are the typical ones I would have in mind. So the relevant one for yesterday's talk would be chain complexes over Q, or maybe rational spectra. I could be talking about spectra. Okay, so this is different notation than the previous talk, but I'm so used to it, I'm not going to change it now. So this means spectra. It could be some localization of spectra. It could be maybe mod R for R, a commutative ring spectrum, etc. These types of things. Okay, so generally the assumptions I'm going to need on C are the following. These are all examples of those. So C is going to be a stable, presentable. So if you don't know what that is, just think sufficiently many limits and colimits. Stable, presentable, symmetric monoidal. They need a tensor product in order to do algebra. So the symmetric monoidal, and I'm going to assume that the tensor product is compatible with colimits. Okay, so tensor product preserves colimits in each variable separately. Yeah. Bigger. Okay. Yeah, I'll write bigger. Thanks. Okay. Should I write this again, or is this okay? Anyway, it's a stable infinity category with lots of great properties. Okay. Anyway, so all of these are examples, at least if you require that your localization was compatible with smash products or something like that. But that's usually the case. Oh yeah, it is turning smaller along this line. Yeah, okay, that's pretty bad. Okay, I'll really try. Okay, right. So this is the generality that I'd like to work in, because it will cover all of the relevant examples. So let me just define operads and co-operads for you in this generality. So there are many ways to do this. So in particular, if you sort of check the collected works of Rune Haukseng, you'll find like 4 or 5 different ways. Let me pick one. So I want to, for the purposes of this talk, or this lecture series, I want to think of operads as just symmetric sequences with some extra structure. So I'm going to pick that approach. So I'm going to write symmetric sequences in C. By definition, this is going to be the infinity category of functors. Functors from the category of finite sets and bijections. Okay, so this is finite sets and bijections to C. Okay? So you could just, if you wanted to, replace finite sets by a skeleton of it. So you just take the sets like of the form 1, 2, blah, 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 up to n for all natural numbers n. You include the empty set and automorphisms of those. Okay, so you could think of a symmetric sequence so an object of this infinity category, you could just think of it as, as a sequence an, n ranging over the non-negative integers, where each an is equipped with an action of the symmetric group sigma n. Okay, so an is acted on by the symmetric group. All right, so that's the category of symmetric sequences, and this category is relevant for the following reason. It acts on the category C in the following way. So to any symmetric sequence A, we can associate a functor from C to itself that I'll call FA. So this is a functor from C to itself, and what does it do? It just takes an object X and it sends it to, well, the sort of the usual formula you'd write down for the free algebra for an operad. Okay, so you send it to the infinite sum of an tensor x to the n, and then you take the homotopy orbits of this expression. Okay, so in this sense, the category symmetric sequences in C acts on C. All right. Functors from C to C, there's an obvious way to compose these, and there's a corresponding structure on the category symmetric sequences. You can compose symmetric sequences, right? So there is a monoidal structure which I'll denote like this, right? So this is like a little circ. So this is called the composition product. So on category symmetric sequences, so this thing, as I just said, it's called the composition product. Oh, I did not switch the camera, did I? Sorry for everyone who's watching the video. Okay. Right, so there's a monoidal structure here such that this assignment, this action that I wrote down, is actually monoidal, right? So that this functor that goes from symmetric sequences, I'll raise the board a little bit. So from symmetric sequences to endofunctors of C that sends A to FA is monoidal. In other words, it sends the composition of symmetric sequences to the composition of functors, right? I'm thinking, the monoidal structure I'm thinking of here is composition, of course. Right, and that's why it's called the composition product. Okay. I'll say something about this composition product in a minute because there's sort of a funny uh, abstract sort of higher algebra style way of setting it up, which for some reason I couldn't really find in the literature, at least not in this context, but it's convenient. Let me maybe, just to be specific, give you a formula for the composition product. So if, in the special case that A and B have no zero term, and this is going to be the case I'm interested in anyway, so let's just assume for a moment that A and B have nothing sitting in degree 0, then you can write a particularly simple formula for the composition product. And actually, A composed with B, evaluated on a finite set I, turns out to be described by the following formula. It's a direct sum over, well, you take a direct sum over equivalence relations on the set I. So let's call those E. So, yeah, okay, the subscripts are small. That's how subscripts are. So this is equivalence relations. On I. And then what you do is you take A of I modulo this equivalence relation, and then you tensor with a tensor product over all of the equivalence classes. Let's call them J. So these are the equivalence classes for this equivalence relation, and you do B of J. Okay? And I claim that this, well, at least this gives a formula for the composition product of two symmetric sequences, and you can check that it corresponds to what I claim down here. If you include zero terms, I mean, you can also write down a formula, but the formula just gets a bit more awkward, and you have to take some orbits for symmetric groups somewhere, and I don't really care about that for the purposes of this talk, so I don't want to bother. It's definitely not symmetric, yeah, very much not. You can also see that from this formula, right? But also, it's like, I mean, the composition of functors, of course, is not symmetric, so. It's not the day, I will say something about the day convolution, actually, but this is not the day convolution, yeah. Okay, so, right, if you have this monoidal structure set up on symmetric sequences, it makes sense to speak of monoids and comonoids. Yeah, question? So the second part, should there be a tensor product? Is that? This is a tensor product, yeah. I take the tensor product over all the equivalence classes for the equivalence relation E, right? So these J's, they're subsets of I. Exactly the equivalence classes for E, and for each such equivalence class, I take B evaluated on J, right? B is a functor on finite sets, so. Okay, all right. Other questions about this? All right. So what you can do here is you could just use the usual definition of operads and co-operads. You could say an operad in C is it's an associative algebra, or a monoid, if you want, in this infinity category of symmetric sequences. Okay, and a co-operad is just the dual notion. So a co-operad is a co-algebra in this thing. And if I wanted to find things in this particular way, it is important that C was stable. Otherwise, this wouldn't really be the right thing to say. I would have to, you know, swap out sums for products and blah blah blah. But if we're stable, then finite sums and finite products are the same, so we don't really mind. Okay. So maybe said a bit more informally, an operad O is really just a symmetric sequence equipped with a bunch of composition maps of the following kind. And this is just an unraveling of the definition that I wrote down. You just have maps of this sort. So if I have like n-ary stuff, and then I specify n different like operations with k1 up to kn inputs, then there should be a composition here, or a multiplication that spits out something with sum of the ki many inputs. So there are these kinds of maps plus all sorts of coherences for these, right? These multiplications are supposed to be symmetric and associative in the appropriate way, blah, blah, blah. All right. So that's the definition of co-operats and operats, and since, well, I think I have some time, so I just wanted to do a very brief digression on this composition product, because as I said, yeah, there exist several versions in the literature, and I just want to suggest an easy one. Hey, wait, oh, yeah. So here's a little sort of digression on circ, on this composition product. So here's one funny way to construct it. What you do is you could look at the category of symmetric sequences in just the infinity category of spaces, okay? So look at functors from here to here. So this is symmetric sequences in spaces. And as was already remarked just now, there's another way to make this a monoidal category. You could give this the day convolution product, right? So this is symmetric monoidal under day convolution. Right, so just to remind you, what is the day convolution? Well, it's essentially the thing that if you had two symmetric sequences A and B evaluated on a finite set I, it would just be the sum over decomposing, all the ways of decomposing I into two subsets. I1 and I2, and then you take A of I1 tensor B of I2. Okay, so that's the day convolution product on this category. It's symmetric monoidal. So if you take this category, you equip it with this day convolution product, then it has a universal property. Namely, it's actually, well, there are a couple ways to say this, but finite sets and bijections itself, if you think about it, is actually the universal example of a symmetric monoidal category on one object. So symmetric monoidal functors out of this category are just the same as, you know, specifying an object, so evaluating at the one object, because, you know, any finite set is a disjoint union of copies of one. So if you know where to send the one point, the singleton, then you know where to send everything. So that's the universal property of this guy. Now this, you know, taking functors into spaces is just, you're just freely adjoining colimits to something, right? That's what, well, I mean, strictly speaking, I would have to say pre-sheaf, so I'd have to put an op here, but this is a groupoid, so let's ignore that. So this, with this day convolution product, this should be the universal example of a symmetric monoidal infinity category on a single object, which is also presentable, okay? Or it has colimits, whatever. So this symsec S with this day convolution, is the universal presentable symmetric monoidal this is getting smaller, so here's a big infinity for you. Symmetric monoidal infinity category on one object. Right, so what that means, it just means that if you were to look at functors out of this into some general, let's say, presentable symmetric monoidal infinity category D, and you ask that these functors preserve colimits, so let's denote that with an L, and that they are symmetric monoidal, so they're compatible with the tensor product, then actually this, sort of by evaluating at the one-point set, so to speak, so evaluation just gives an equivalence from this infinity category to D itself. Right, so specifying a colimit preserving symmetric monoidal functor out of this is the same as specifying an object of D. Okay, fine. What's the point? Well, you can now just take D to be symmetric sequences in S, okay? right? So if you do that, then the right-hand side is the category that we're interested in, and the left-hand side obviously has a monoidal structure, okay? So then the right-hand side becomes symmetric sequences in S, and the left-hand side becomes, well, it's endomorphisms of symmetric sequences in S, so functors from this thing to itself that preserve colimits and are compatible with this day convolution. But whatever, this is clearly monoidal, right? This has a composition. So this is monoidal. So this is monoidal under composition. All right. So yeah, you have a monoidal structure on the left-hand side. This is an equivalence of infinity categories, so you can just transport it over to the right-hand side. And that's one way to get the composition product for symmetric sequences of spaces, but then you're essentially done, because actually there's just a standard trick to now get it for a general infinity category. So for general C, well, either you could try to sort of do some C linear version of the same story, or you could just say directly, it's essentially doing the same. But symmetric sequences in C is the same as the tensor product, well, but of presentable infinity categories. Symmetric sequences in S and C. So this is like Lurie's tensor product. On presentable infinity categories. Okay. So this is the thing you'd expect. Like a functor, a colimit preserving functor out of the tensor product is the same as a functor out of the product that preserves colimits in each variable separately, like a bilinear functor, so to speak. Anyway, so this immediately transports this monoidal structure from here to anything of this form. So like this. Okay. Right. That's the end of this digression. Right. So, well, once you have operads, of course, the main reason to get involved with operads in the first place is to be able to define algebras, right? So let me just quickly recall that. Sure. Question. Yeah. Well, the question is, does symmetric sequences in C have a similar universal property? Yes, it essentially has the same universal property if you make everything C linear. So like, you can work over the base categories. Like C is nice enough that you could, because it's symmetric monoidal presentable, that you can do C linear everything, and then you could say the same stuff. But yeah, this is a bit quicker, but it amounts to the same thing. Yeah. Does that answer the question? All right. Other questions? No? All right. Okay, so what I was going to say is, so of course we want operads so that we can define algebras. So an algebra for an operad O, well, one way to say it is it's just an algebra for the corresponding monad. F sub O. So F was this functor that I associated to a symmetric sequence. If O is an operad, then because this this functor that assigns FO to O is monoidal, it will send an operad to a monad. It will send algebras to algebras. Okay. So in particular, in O algebra, if you unpack, it's just, well, I shouldn't use the word just all the time. It's an X in C with maps of the form O n tensor x to the n h sigma n to x. Okay, and you could give it a dual definition of coalgebras. There's a bit of care required if you want to talk about coalgebras. So maybe you'd be inclined to say, okay, if I have a co-operad, say Q, then a coalgebra for Q is like a coalgebra for the co-monad f of Q. that's not really right. I mean, that's a definition you can make, and you get some notion, but that's not the notion that deserves to be called a coalgebra. Because, so maybe, warning. So coalgebras for f of q, where say q is a co-operad, these are usually called conilpotent and divided power coalgebras. Okay. So what's the reason for that is that, well, you know, if you use this as your definition, then, you know, a coalgebra would be something like a y equipped with the map to fqy, and this is just the direct sum over like qn tensor y to the n h sigma n. And then these adjectives here, this conilpotent refers to this direct sum appearing, and this divided power thing refers to these orbits appearing, because really a coalgebra, just a coalgebra, sort of should be defined as a y with maps y to qn, y tensor n, and then you'd like these maps to be sigma equivariant. So if you ask for these maps to be sigma equivariant, sigma n equivariant, that's the same as asking that you get a map to the homotopy fixed points here. So that's somehow the more natural thing to put there. And then it's a collection of maps like this plus some coherence between these maps. Okay, so let me be vague about what the precise coherence is, because there's no need to get into it now. But this coherence, you know, in particular, it's just a collection of maps like this. So the natural thing to write would be you'd have a map from y into the product over n of all these things. And here we're asking that it factors to the direct sum, which is extra structure on a coalgebra, and that's this conilpotence that I put up there. So, yeah, let me just keep that as an aside. I don't want to stress this point too much, but it's sort of important to be aware of the distinction. So this seems a bit asymmetric, and fundamentally the reason for this asymmetry is that we started with a tensor product that was compatible with colimits in each variable, but not with limits necessarily. And that's where this sort of thing, that's where the asymmetry in the end comes from. You could of course ask that your tensor product was also compatible with limits, but your list of examples would be pretty thin, so it's just a boring thing to consider. Don't do it. Right. So now that we have this, it makes sense to start talking about Barcobar duality. So now that I've defined operads and co-operads as certain associative algebras and co-algebras, we can apply sort of a general formalism of Barcobar duality to these. And for this particular exposition, let me just, I mean, there are many, many versions and precursors of Barcobar duality. The version I want to use is one that's written up by Jacob, I think in DAG 10 originally, if you wanted a reference. It's also in higher algebra, surely, somewhere. So he develops this extremely generally. Like Barcobar duality classically is something that was invented and created in the DG context, but we want something a bit more general here. And it turns out that Barcobar duality is extremely general. So for D, just any monoidal infinity category, and maybe let's assume it has limits and colimits. You can be a bit more precise about what you need precisely, but there's always an adjoint pair of the following kind. So there is an adjunction that goes between algebras in D. These algebras should be augmented, so they have a map to the unit for the tensor product, and co-associative co-algebras in D, which are co-augmented. And this adjunction, the functors are usually labeled bar and cobar. And you can give explicit formulas for what these functors do. So the bar really is the bar construction. Okay, so bar A is really, it's the geometric realization, meaning the co-limit of a certain simplicial object. So it's a simplicial object that would be commonly denoted like this, so as a two-sided bar construction. So here, this boldface 1 is just the monoidal unit of this category. This is the two-sided bar construction of 1 and 1 over A. So what this is, by definition, is just the co-limit of a simplicial diagram that looks like this. So you have 1, there's A, the two maps are just the augmentation of A, and then you have A tensor A. So again, two of these maps, they use the augmentation, and the third map uses the multiplication on A, and then etc. Right? There's sort of an obvious way to continue this diagram. It's the co-limit of this diagram. And the cobar construction has a dual formula. So cobar C, it's the totalization of some co-simplicial object. It's just the limit of like this. Okay. Okay, so the question is, in the beginning I assumed C to preserve the tensor product on C to preserve colimits in each variable separately. Is that what I need here? Actually, I don't need it for what I'm saying right now. It is a colimit, yeah. It doesn't have to do that. Sometimes it's convenient that it does that, but it doesn't actually have to for this particular thing that I just wrote down. It's a bit tricky. But I mean, because also if that were actually true, like if I really needed the tensor product to preserve this colimit, then why would this be a valid formula somehow, right? I mean, there's a duality here that if you're careful about setting this up, then the assumptions you need on D are really extremely minimal, and I don't need to assume compatibility of the tensor product with these constructions. Like so? That's correct, yeah. I've used additivity to define, I've used the fact that finite products are finite coproducts to make my definition of co-operand a reasonable one. But you're right, I haven't used stability yet. I will use it very soon. I'll point out where it's used, okay? All right. So maybe, you can write down these formulas for bar and cobar constructions, that's fine, but of course usually proofs in the infinity categorical setting don't go by writing a formula that doesn't, I did switch the screen just now. Oh, really? Oh, thanks. Can you stick around? No, okay. Okay, so, these formulas are fine, but, one thing that, for example, isn't clear when you write down this formula for the bar construction is that thing indeed has some coalgebra structure, right? It's how do you get a coalgebra structure from that formula? So you have to do something a bit more clever. So I just wanted to, it's maybe a bit cryptic, but let me just mention the proof idea very briefly, because I think it's a very cute idea, and to me at least it was very illuminating. So the proof idea here is to do the following. To prove that there exists such an adjoint pair, you do the following. You identify both of these spaces. So you identify maps of augmented algebras between A and cobar C, and map of coalgebras. So to prove that there exists an adjoint pair with the desired properties, you prove that both of these spaces are equivalent to well, a single space that sort of isn't biased towards one of the two sides, namely the space of lifts of the pair A comma C to an augmented algebra of the twisted arrow category. Okay. Of D. Yeah. Okay. The pair A comma C. Yeah. Did I? Sorry. Here I messed it up. Was this the question? All right. Thank you. Yeah. This was a typo. All right, so this is maybe a bit cryptic, but I just wanted to put it out there because when I was sort of your age, now it sounds like I'm really old. No, when I was a PhD student, I was trying to understand something about Barcobar duality and reading the DG literature, and I got a bit confused because it's all about things like twisting cochains and these very specific things that are very useful because you can calculate with them. But I had a really hard time sort of wrapping my head around, the conceptual meaning of a twisting cochain. I couldn't figure it out. And so then Jacob at some point explained this, and it was very helpful to me because this is really, to me at least, this gives some more meaning to what a twisting cochain really is. It's sort of lifting this structure to an algebra in the twisted arrow category. Anyway, you can think about that on your own if you want to. And yes. Oh, sure. Okay. Yeah, my grammar is a bit lacking. Yeah, okay? Is that? All right. Yeah, it's like an algebra object in the twisted arrow category. So it's a map from A to C plus a lot of structure on that map. Okay. Right, great. So we're going to apply this Barcobar duality to the particular example that we care about here. So we apply this to D is symmetric sequences in C. Okay? So this Barcobar duality is going to give us an adjunction between augmented algebras and augmented coalgebras in symmetric sequences, and that's what we were calling operads and cooperads. So we get operads in C, I'll denote that like this, and well, they're augmented. So they have a map to the unit, which is just a symmetric sequence that has 1 in degree 1 and zeros everywhere else. And so it's like bar and cobar. And then here you put cooperads, augmented in C. Okay? So in this generality, there is a bar-cobar adjunction relating operads and cooperads. Okay. And it turns out this adjunction has really excellent properties, so let me state a theorem. So I'm not sure about how to attribute it exactly, but like in the DG setting, there are lots of precursors to this. Like this, I mean, this starts maybe in the work of like Ginsburg, Kapranov, and Getzler-Jones. And then in the setting where C is spectra, there's a proof by Ching. Maybe I'll just write all of their names. Ginsburg, Kapranov, Getzler-Jones. There's Michael Ching, etc. This is close to being an equivalence. So if you restrict to reduced operads and cooperads, okay, so reduced here for me means O of 0 is 0, and similarly for cooperads, I'll just use Q as a generic letter for cooperads, plus in degree 1 we just have the unit, or something equivalent to the unit, it doesn't really matter. So for these things, this adjunction restricts to an equivalence, so you don't lose any information passing back and forth. So this gives an equivalence. Okay, so as I said, they prove this in specific settings, but in particular, Ching's proof in the setting of spectra is sort of general enough. All of the ideas there you can carry over to this setting and really give a proof in the general case, so without too much of a hassle. So this is true, and this is really useful because it's yeah. Yes. Oh, thank you. Yeah, excellent point. This really requires C to be stable. This is where I'm really using it. Thank you. Yeah, excellent point. Okay. Other questions? All right. So just a few quick examples of how this Barcobar thing plays out in practice. So maybe the simplest example where you can also really calculate things quite explicitly is if you take the associative operad, which you can easily define in any monoidal category, and maybe I should be precise, like I mean the non-unidal associative operad, so you chuck away the operation in degree 0, because otherwise it isn't reduced. So if you take this one, then the bar construction of this is, well, it's essentially the associative co-operad, meaning you just take the linear dual of the associative operad. So this is the linear dual of the associative operad again, at least up to a degree shift. There's a degree shift by 1, but let's not be too bothered by that. So this is what people mean when they say the associative operad is self-dual. This is one way to articulate what they mean. The other one is if you take, let's say, the En operad, so that's n is 1 would be the reproduce this. And let's say in spectra, okay? So I'm thinking En is an operad in spaces, just a little disks operad, and I take a suspension spectrum to get an operad in spectra. Then again, this thing is self-dual in the sense that bar of O is the, well, what does linear dual mean for spectra? That means Spanier-Whitehead dual. So it's the Spanier-Whitehead dual of En. Again, up to a shift. The shift is by n this time. Okay, so in this generality, this is a pretty recent result of Ching and Salvatore. But this has many precursors. So over Q, I think you'll find this in Getzler-Jones, and then over Z, it's a result of Benoit Fraisse, I believe. Okay. A final example, what happens if you take the commutative operad? So let's take C to be something DGE. So let's say chain complexes over a field, or maybe chain complexes over a commutative ring. In that case, the bar construction of the Lie operad is well studied. So you can take bar construction of the Lie operad, which, well, first of all, if you work with this base category, it should be clear how to define the Lie operad. Its bar construction is the commutative co-operad. So meaning the linear dual of the commutative operad. So that just has the tensor unit in every degree, up to shift. Again, there's a degree shift by 1. Okay. So the question is, what happens if you don't do this additively, if you do the bar construction for spaces? I mean, like, if you were to, like, the bar construction is something that, it uses tensor products and colimits, so it's like compatible with the suspension spectrum. So if you do this for the En operad in spaces, then you get something in spaces which, once you take its suspension spectrum, it is the En co-operad. So like the bar construction in spaces is in some sense already the correct one, but talking about co-operads in spaces is really awkward because of this non-additivity. So like it's not wrong, but it's not going to be, and you can't go back. Like if you then apply the co-bar construction to that thing, you just get some, I don't know, some junk. Yeah. All right, so, but this last point at least inspires the definition of the Lie operad in general, because, why restrict ourselves to a sort of a linear setting? I mean, the commutative operad, or the commutative co-operad, is surely something we can always define, because you just need to know what the tensor unit is, which, Yeah, thank you, very good, yeah. All right, cool. So here's just the definition of the spectral Lie operad. So the spectral Lie operad, L, I'll use this Blackboard bold, L, is defined to be co-bar of COM, where this is the commutative co-operad, but now in the infinity category of spectra. Okay. I don't. Yeah. The question is, do I shift it? And I don't. But I'll. Okay. So you can. I mean, you can shift this thing so that its homology really is the ordinary Lie operad. But actually, that's. Yeah. Okay. There are different tastes in this, and I don't like to do that because I think it's sort of more natural to have to bracket in degree -1 for various. But it doesn't really. It's cosmetic. It doesn't matter in the end. But there's certainly like I think Ben Knudsen would disagree with me. He likes to shift it to degree 0, and I sort of don't. It's not a. It doesn't really matter. No, I mean under connectivity hypotheses it would. Like if your terms are sufficiently connected so that the terms in the Kobar construction become more and more highly connected as you move to the right, then yes. Otherwise, there's no way to commute rationalization past the limit. But if the limit is like degree-wise finite, then there's no problem, and that's what you would get if you assume some connectivity. Okay. Right. So this is the definition. Let me just state some facts about this operad. So first of all, so this is some operad in spectra that you should think of as an enhancement of the ordinary Lie operad. And enhancement in the following particular sense: if you just take degree-wise the homology of these spectra, you reproduce the ordinary Lie operad. Okay. So H star of L. This really is the ordinary Lie operad, but shifted. And shifted in the following sense: the bracket will now live in the homological degree -1. Okay, so bracket in homological degree -1. Okay, again, as I was just saying, you could get rid of this shift if you don't like it by redefining, but yeah, let's not. So that's property 1. Property 2 is the terms in this operad are really very explicit. You can just say what they are. So first of all, if you want to be sort of simple-minded, if you disregard the sigma n action, which you shouldn't do, but this spectrum really is very simple. So disregarding the sigma n action, this Ln is just a wedge of spheres. So this is a sum of n minus 1 factorial copies of the sphere spectrum living in dimension 1 minus n. Right, this is also what you'd expect based on this. Like you want, if the bracket sits in degree -1, then like the 2-area operation should sit in degree -1, and if you start composing, like a 3-fold bracket should live in homological degree -2, etc., etc., etc. A bit better is to just actually describe the homotopy type. So, and that's where the partition complexes come in. So let's write part n for the poset of partitions. Oops. I should say non-trivial, non-discrete partitions of an n-element set. All right, that's a poset, so you could take its classifying space, right? You think of it as a category, take the nerve, that's a space, or simplicial set, whatever. Then you can describe this Ln as, well, essentially the Spanier-Whitehead dual of that space, but you have to do a few things to it. So you take the classifying space of this part n, you suspend it once. So this is the unreduced suspension, because there isn't a base point, so I can only do unreduced suspension. Then you suspend it again. Now you could take the reduced suspension. And this is a pointed space, so you could take its Spanier-Whitehead dual. That's a spectrum with a sigma n action, like sigma n just acts by permuting these n symbols. And that's what this is. Maybe I should attach Qing's name here. Did I not do that? Yeah. No, we should, but yeah. Thanks for stressing that point. Okay. Maybe another remark. I'll just make it verbally in the interest of time. another important occurrence of this L, and also the reason for Ching to be interested in it originally, is that it occurs as the Goodwillie derivatives of the identity functor on spaces. So if you know about Goodwillie calculus, then you'll probably know this too. But yeah, if you compute the Goodwillie derivatives of the identity functor, you get exactly these ln's. And actually, one way to prove that is sort of through Kuzu duality. So you show that if you differentiate the identity functor, then you might as well have differentiated the sort of the Bausfield-Kahn resolution of the identity, right? The functor Q, so loops infinity, sigma infinity, gives a cosimplicial resolution of the identity. And you differentiate that, and you just check that the derivatives of that cosimplicial object are exactly you just get the Kobar construction of the commutative co-operad, essentially because the derivatives of sigma infinity, loops infinity are the commutative co-operad. And then, so just, yeah, anyway, you know, if you know Goodwillie calculus, then you know this, so I don't have to tell you, and if you don't, then I'm telling you nonsense. So let's go to the next board. Oh, that's not right. All right, so what I want to finish on is telling you what this means for O algebras and BO co-algebras, because that's the whole point in the end. All right, so from O algebras to BO co-algebras. So if we have one of these augmented operads O, right? So I have an operad O with an augmentation to the trivial operads. Let's call this augmentation epsilon. Then this augmentation gives an adjunction on categories of algebras. So I could look at alg O in C, and I could look at alg 1 in C, but algebras for the trivial operad, that's really just C. I mean, that's not specifying any data other than an object. And this epsilon, you know, I could just, let's say, restrict scalars along epsilon. So there's like just restriction along epsilon. Gives me a functor from right to left, which, if you think about it, it just takes an object in C and it equips it with the trivial O algebra structure. All of the multiplication maps other than the unit are just 0. Right, so this is really, you should think of this as the trivial O algebra functor. And just for formal reasons, or if you could also just construct it, this has a left adjoint, let's call it epsilon shriek. And by the same logic as yesterday, you know, it's the left adjoint to the trivial function. I just want to call it indecomposables, right? So epsilon shriek takes the indecomposables of an O algebra. Or you'll also see this being called topological André-Quillen homology, or topological André-Quillen O homology, or something like that in the literature. It's the same notion. Okay, so as with any adjunction, you know, just by general nonsense, this E shriek of X is a co-algebra for the comonad that comes out of this adjunction. So this is a co-algebra for epsilon shriek, epsilon upper star, which is some comonad, but you can very explicitly identify this. So if you apply this, so you take an object of C, you make the trivial O algebra on it, you take its indecomposables, then you can check that this just looks as follows. This is the direct sum of the following terms, bar construction, oh, sorry, I abbreviated bar to B, I hope that's okay. This is this, okay? So in particular, this epsilon shriek of X, it's always a divided power BO co-algebra. I mean, it's even a conilpotent divided power BO co-algebra, but technical reasons, I actually like to ignore the co-nilpotence here. But okay, so just from general nonsense, you get this fact that that these indecomposables have this co-algebraic structure. Maybe one thing I should say, this divided powers, I'm keeping track of it here, but for the purposes of this lecture series, we don't really have to. Like over Q, it doesn't matter. Over the rationals, the orbits and fixed points with respect to a finite group are always canonically isomorphic, so we don't have to distinguish. And even in this periodic setting, so in Vn periodic spectra, or let's say Tn local spectra, Kn local spectra, whatever, it's a theorem of Kuhn that, again, the same is true, that orbits and fixed points are the same. So this, you can safely ignore this divided power junk if you wanted to, for the purposes of this course. Of course, lecture series thing. Okay. Got the right board? Yeah. Okay, so what you get, so the upshot of this discussion is the following. You get an adjunction of the form alg O C and coalg BO C, and let me just put these divided powers here to be precise, but as I said, we don't really have to keep track of them here. And here we have this indecomposables that I just introduced, and this right adjoint admits a very dual description, and I'm just going to call it prim for primitives in the same way that I did yesterday. It can be defined entirely dually to what I defined over there. So there's an adjunction like this, and the crucial question about this adjunction is, well, first of all, I should state this is usually not an equivalence of infinity categories, almost never really. But you can ask on what subcategories does this restrict to an equivalence? So, I mean, yesterday we saw a particular example, namely Quillen's result, that said, if we take Lie and Com and we restrict to connected and simply connected, then this becomes an equivalence. That's one example of an answer to that question. But there turns out to be an optimal answer to this question. That answer is this. So this gives an equivalence between this subcategory of nil-complete, I'll define the term in a minute, between nil-complete O algebras and co-nil-complete BO co-algebras. So another way to say it is if you carefully investigate the unit and co-unit of this adjunction, you get some notion of completion and co-completion of algebras and co-algebras. So yeah, I have like 1 minute, so let me use that 1 minute to tell you what completion is, to at least give this statement meaning. Okay, so completion is the following. So what you can do for any operad O is you can truncate it. You can take the n truncation, So this is just the operad where you set operations with more than n inputs to 0. So this is just O of k. K is less than or equal to n, and it's 0 if k is greater than n. So this gives you, well, there's a map from O to tau n O. That's the truncation, and this gives an adjunction between O algebras and tau n O algebras. Just again, restriction and push forward. And let me just write the following for the unit of this adjunction. So if I have an O algebra X, then I can pull it through. I could push it forward and then pull it back and to get a new sort of truncated O algebra X. And I'll write it like this. So I write this for the unit of this adjunction. Okay, so this is sort of the universal thing I can build from X by killing all operations with more than n inputs. Then the nil completion, or you could say the nilpotent completion, but just abbreviated it to nil completion of X, is by definition the map from X to the limit over n of the Tn x's, okay? And in that theorem, I'm calling an algebra complete if this nil completion is an equivalent. So if x is equivalent to its nil completion. And you can do this, you could dualize everything I put on this board for a co-operad, like there's some truncation, but now it maps in from the left. You can sort of base change along that truncation. You get some filtration, some tower of things mapping into a co-algebra, and the co-limit of that filtration would be the co-completion, or the co-nil completion of a co-algebra. Okay, and the claim is this Kuzu duality, in this generality, it always restricts to an equivalence between these complete and co-complete things. And you can use that to, for example, reprove something like Quillen's theorem. Like if you wanted to get Quillen's result out of this, then what you'd have to check is that, in particular, connected Lie algebras and simply connected co-algebras are complete and co-complete. And actually, that turns out to be very simple, because if you look at these maps, x to t and x for like a connected Lie algebra, then it turns out this map is just n connected if the original Lie algebra was connected. So the connectivity of this map goes to infinity as n goes to infinity, and that's it. Like that's the style of argument that you can make. All right. Yeah, time's up, so I'll stop there. David? Yeah. Yeah, so the question is, in the co-nil complete, does the truncation go the other way? No, you don't truncate below, you truncate above. But for a co-operad, you get maps in the other direction. Oh, this is the wrong chalk, I don't want this. If you have a co-operad Q, then you could sort of, you get maps that I like to denote tau nq to Q. But this tau upper nq is defined by the same formula, but it's just